Now, endocrine. We've got a lot going on here with the endocrine system, but again, like I said yesterday, it's all about the organ and where is it? What does the organ secrete? You got to know what it secretes. Yeah, there's a bucket load of them, but you got to know. You got to know. Okay? You don't have to necessarily know the effects right now. The effects we'll get to later on when we get into the appropriate chapter. Let me say that again. If you're panicking because there's like almost 200 slides, don't. This is a reference for you. Okay, so endocrine. This happens to be one of the shortest chapters, but they put a whole lot of slides on there. All right, so what is it? Well, the organ. What does it secrete? We need to know what that organ secretes. So I'll blast through the slides, stop it where we need, I'll explain it, and then blast through the slides, stop where we need to explain it, and that's the way we're going to set it up. Now, the final thing is, what is the makeup? What is the makeup of those hormones? And unbelievably, those hormones are going to have a specific type of an effect, which is part of the makeup, which you need to know because we're actually going to talk about that as we move through other chapters. So, organ, where's it at? What hormone? And then the makeup of the hormones themselves and their generalized effect. And I'll explain that because some are humoral, some are hormonal, and some are neural. Okay? And because I say it like that, you think about it, humoral, hormonal, and neural. Well, let's just grab our brains for a second, shake it up real quick, like a snowball, right? The snowy village, shake it up for a second and think, wow, we know this, right? Neural. Hypothalamus, infundibulum, pituitary. So when I say it like that, you shouldn't panic. You should be like, yeah, we went over this. Neural. Yeah. The hypothalamus through the pituitary, that's neural. Isn't that whole thing called a endocrine neuro gland? It is, bless you. Okay, so, don't get sketched out because it's actually not that hard. And this is where it starts getting fun. This is where you guys start asking the right questions, start having a lot of fun with the endocrine system. Now, endocrine, oh gosh. There's nothing really fun about it in the sense that we're like, oh yeah, we can feel our heartbeat, or we can breathe, or we have a pulse. But it is fun because this is what controls you. Whoa, that's right. Nervous system and endocrine system control you. Everything else is being controlled. Those two things will control you. They'll control you. Okay? So, let's just add. What if I gave you a big old shot of epinephrine right now? What would you do? Would you just sit there like a Hindu cow, or you'd be like, woohoo, endocrine system? Yeah. And that wasn't derogatory. If you've never seen a Hindu cow, they just sit there. They just, yeah. I try not to use it on a woman because you call them a cow, man, you're done. Yeah. All right. Endocrine system, regulate long-term processes. Yes, it does. Growth, development, and reproduction. So obviously from 0 till you're out of puberty, you got a lot of growth going on. You got a lot of development going on. But let's go before 0. Reproduction. That's right. Before 0. You got nine months of chemicals going on there. 9 months of chemicals going on. Uses chemical messengers to relay information and instruction between cells. Between cells. Okay? Because it's endocrine, it's within. All right? So, we're going to start off with just some of them, and this helps you out where they're found. Where they're found. So, hypothalamus, production of ADH and oxytocin, ADH, antidiuretic hormone. By the way, you need to know what these abbreviations mean. okay? When I said you need to know the hormone, guess what? Yeah, you gotta be able to do the abbreviations. So, antidiuretic hormone and oxytocin, we're talking about pregnancy here, okay? And regulatory hormones, and then we're gonna drop down to the pituitary gland, okay? Anterior lobe, this is extremely important. Anterior, front lobe, anterior lobe, ACTH, TSH, GH, PRL, FSH, LH, and MSH. You know what, just because of that, I'm gonna help you guys out. I'm totally gonna help you guys out. You guys ready? Here comes the help. This is me just caring about you. Okay, this is how much I love you guys. The H in all of these means hormone. All right, so there you go. I helped you out. So it means hormone if you didn't know. So just see that's how much I care. Hormone. What kind? Well, adrenal corticotropic hormone, thyroid stimulating hormone, growth hormone, prolactin, follicle stimulating hormone, luteinizing hormone, and MSH is actually new. Okay, and we'll wait to get to that one on MSH. Posterior lobe, oxytocin, already talked about it. Antidiuretic hormone, talked about it. Okay, pineal gland, have we heard this before? Yeah, melatonin. Parathyroid gland, well, yeah, bone development, parathyroid hormone. Okay, parathyroid hormone. Look at that. Nice. Okay, thyroxine and triiodothyronine. Okay, that's a fun one to say. One of the very few words where you'll see two I's together, triiodothyronine. And then calcitonin, what is that? Bone development, right? Remember breakdown and build up of bone? There you go. Okay, the adrenal gland, well, didn't we just go through that? The adrenal medulla, epinephrine, norepinephrine. So there's something you guys already know. I talked about the cortex, so cortisol, corticosterone, aldosterone, salt-loving hormone there, okay? Androgens, you might as well just say we're talking about development there. Okay? Pancreatic, insulin and glucagon. All right? Key pituitary, and then we go down to MSH, melanocyte stimulating hormone. Now, did you guys know that this was never in the books? Never in the books about 2.5 years ago?
What?
Melanocyte stimulating hormone. Okay, so they do spell them out for you, so when I went through them and you were freaking out, don't worry, they have them labeled for you. It's good to go. You're solid. All right? Now, check this noise out. Organs with secondary endocrine function, which is the reason why we're going to talk about these hormones specifically when we get to the chapters that they're in. Much better that way. You'll actually understand them and use them better that way. Well, the heart, ANP, okay? BNP, brain natriuretic peptide. Thymus, thymosin, okay? Adipose, leptin, okay? Think of lipocyte, leptin, okay? Digestive tract, wow, we got a whole bunch of stuff going on here, but the digestive tract gets a little carried away. They don't even put it on here, but let's just jump over here. Glucose and metabolism, glucose and insulin. Okay, when we get to the digestive tract, there's a whole bucket load of hormones. Okay, a whole bucket load of chemicals that we're going to talk about. So much that they don't even put them up here. Kidneys, erythropoietin. We're talking about the development of red blood cells. Calcitrol. Okay, gonads. Well, there's our androgens down below. Okay, we had androgens up above here. So they're matched up. And notice they're giving you the chapters that we're going to actually talk about these. We'll talk about all of these in these chapters. So it's good to know that they're going to link right up to chapters. But specific organs produce specific hormones. And then, of course, they work with other systems to make these hormones work properly. Any questions? All right, good. So, homeostasis and intercellular communication. Well, paracrine, para means beside. Okay, para means beside, so secrete beside. Okay, direct communication, exchange of ions and molecules between adjacent cells across the gap junction occurs between two cells of the same type. Two cells of the same type, highly specialized, relatively rare. Then we come down to paracrine communication, uses chemical signals to transfer information from one cell to cell within a single tissue. Most common form of intercellular communication, right there, paracrine. Endocrine, oh my goodness gracious me, this is the one that we're going to be focusing on. Endocrine cells release chemicals, hormones into the bloodstream. Into the bloodstream. Now technically paracrine isn't part of the endocrine system because paracrine's beside and endocrine's within, yeah. So endocrine cells release chemical hormones into the bloodstream, alters metabolic activities of many tissues and organs simultaneously. So it's not that it's just going to say, I'm going to release this, and I'm only going to affect your heart. That isn't the case. That's not the case at all, because when we release it, which we already know there are different receptors for specific hormones, right? Guys, beta, alpha, muscarinic, cholinergic, adrenergic, remember all of those? Yeah, you might have to go back and revisit those because I'm sure we're going to talk about them again. But what we're talking about here is that we release it into the entire bloodstream, everything is affected by it. And right now, in the morning, is when we have the biggest dump of chemicals. Right now. Okay? If you haven't eaten anything this morning, you're relying on your liver for sugar. Okay? It will affect your ability to concentrate. Just saying, it will. So if you haven't had breakfast or anything like that, it will affect your ability to concentrate because you've got a whole bunch of chemicals going on without the nutrients you need to process everything. Yeah, that's right. Now you're thinking about it like, huh? Yeah. You dump all these chemicals. Well, let's use a pretty good example. You wake up in the morning, you grab all of your vitamins, and you take all of your vitamins, and then you go potty. Is it clear, or is it day glow yellow like her shirt? It's like her shirt. And that's because you have no food in your body, nothing to slow down the process, to help absorb, or anything else. So literally, you've got some really expensive urine. Yeah, because you just sat down on the toilet and peed all of those vitamins out of you. So in the morning, it is very beneficial for you to do what? Eat a good breakfast. Not a lot either. I mean, it can be just a little bit. A banana, maybe a slice of toast. But you need to eat something. Okay? Because we got to help the processing of those chemicals. So target cells are specific cells that possess receptors needed to bind. Read hormonal messages. They have to be able to bind to it. Okay, hormones stimulate synthesis of enzyme or structural proteins, increase or decrease the rate of synthesis, turn existing enzymes or membrane channels on or off. So you see why I'm saying don't try to learn everything these hormones do? Because it's not just like, oh yeah, it's excitatory like I asked you. It's a whole lot more. It's a whole lot more, and it takes time to learn all of these. Okay, so gland or organ, where's it at? What hormones does it secrete? And then the makeup of hormones, which we'll talk about. Every little detail it does specifically is too much. We need to learn it when we're in that chapter so you know exactly how it's working. Synaptic communication, ideal for crisis management, occurs across the synaptic cleft. Wow, we know that. Chemical messenger is a neurotransmitter. Well, this is repeat. This is stuff we already know. Okay, this just kind of opens it up for you, gives you a little diagram, says, ooh, here we go, this is what we just talked about. Classes of hormones. This is what I was talking about, knowing the makeup of the hormone. You need to know this. The makeup of the hormone. So hormones can be divided into 3 groups: amino acid, peptide, and lipid. Amino acid, peptide, and lipid. Secretion and distribution of hormones. Hormones circulate freely or travel bound to a special carrier protein. So it's either circulating around by itself or it's bound to a protein to where it can actually do what it needs to do within the body. So all the hormones that you guys know, guess what you're going to have to do? So here's the gland. I'm going to keep saying this because I want to make sure this sinks in. Here's the gland. Here's its hormones that it secretes. What category, class of hormone are those hormones? What category are they? Okay? Amino acids. Well, this is going to break it down for you. So, are small molecules structurally related to amino acids derivatives of tyrosine, thyroid hormone, and catecholamines? Now, this is the first time you guys are hearing this. Catecholamines, but all that is epinephrine and norepinephrine. Catecholamines. How about those catecholamines? In fact, it might get to the point where I'll never even bring up epinephrine again. I might just say catecholamines. Because it sounds better. Catecholamines? That sounds like a cat that has a cold and is mean. Catecholamines. It's a mean cat with a cold. All right. All right. Derivatives of tryptophan, dopamine, serotonin, and melatonin. Okay, so now we've got our chemicals coming out of amino acids. Peptide hormones. All right, so our chains of amino acids, most are synthesized as prohormones. Pro just means before. Good, good. Okay. Inactive molecules converted to active hormones before or after they are secreted. So in other words, by themselves, kind of useless. It's not until they're actually turned on that they're worth something. Okay, glycoproteins. Proteins are more than 200 amino acids long and have carbohydrate side chains. TSH, thyroid stimulating hormone, luteinizing hormone, follicle stimulating hormone. Okay? So are we starting to get a pattern here where we're actually writing amino acids, peptides, lipids, and then writing the actual hormone underneath it so we know which ones they fall in, what class they are? Okay? And if you were to do a Word document with this, literally you could go across the top of the classes and then double box it down below, because then you could put the hormone with its organ right next to it. That'd be the best way to do it, right? Maybe color this, like fill the blocks with a certain color, so that you know that that's the organ it belongs to. So you have the class, the hormone, and the organ that it belongs to. Awesome way to do it. Of course, that's the way I'm thinking. Some way to categorize it so it's easy to study. All right? Short chains. Anti-diuretic hormone and oxytocin. Unbelievably, they come from one specific spot and both of them are together. Okay, didn't we hear that? Something about hypothalamus with this one, right? All right. Small proteins, growth hormone, and prolactin. Now, prolactin is part of pregnancy, growth hormone, obviously, promoting growth in child development, infant and fetal development. Okay, includes all hormones secreted by. Peptide hormones include all hormones secreted by hypothalamus, heart, thymus, digestive tract, pancreas, posterior lobe of the pituitary gland, as well as several hormones produced in other organs, which we're not going to tell you, but we know that there are several other ones. So, again, a chart, class, hormone, where's it coming from? Lipid. Okay? Eco or ico, it doesn't matter how you say it. Cyanoids. Okay? These are paracrines. prostaglandins, prostacyclins. Well, we're not actually going to talk about these until we get into, unbelievably, the blood, cardiovascular system. I'm not going to talk about them at all until we get that. And then when we get there, we're going to keep bringing it up, and I'm going to say go back and reference it. Because I'm looking at that, yeah, there are actually a couple questions about this on that blood test. Because it's about clotting factors. Okay, but the ones you do need to know are steroid hormones. Okay, derived from cholesterol, the reproductive organs, androgens, okay, the cortex of the adrenal gland, corticosteroid, the kidneys, calcitrol. So again, class, hormone, organ, or gland that it's secreted from. Now, they're circulating, because they're circulating steroid hormones are bound to specific transport proteins in the plasma, they remain in circulation longer than secreted peptide hormones. So they're in there for a long time. Okay? And I've already mentioned one, adrenal corticotropic steroid, or excuse me, hormone. Adrenal corticotropic hormone. Adrenal, as in the adrenal gland. Cortical, cortex. Okay? So remember, don't get overly excited when you see a long word. ACTH, adrenal gland, cortical gland. The cortex, the outer husk of the adrenal gland. Free hormones, okay, remain functional for less than 1 hour, diffuse out of the bloodstream and bind to receptors and target cells, are broken down and absorbed by the cells in the liver or kidney. They are broken down and absorbed by the liver and the kidney, after broken down by enzymes in plasma or in interstitial fluid. So, free hormones circulating around. When they're done, when they've reached their target organ, we're actually going to just break them down. And you're going to find out that the liver actually breaks down a lot of different things. A lot of different things. Thyroid and steroid hormones remain in circulation much longer, but we just saw that on the previous slide. They enter the bloodstream, more than 99% become attached to special transport proteins. Bloodstream contains substantial reserve of bound hormones. So, a hormone that just goes out and that binds to a specific target, pretty much gone in about an hour, no big deal. A hormone that goes out and circulates throughout the bloodstream, bound to a protein, a long period of time. Now, mechanisms of hormone action. Now, I want to just stop here for a second, and I want you guys to visualize different receptor sites, different binding sites. It has to bind. If it binds, then it can create something. It can do something. So, hormone receptor sites. Not always going to bind, but the interesting thing is if we don't have enough receptor sites, we can make some. If we have too many receptor sites, we can get rid of some. How would that be beneficial to us? How would making receptor sites and getting rid of receptor sites be beneficial to us? If you're only getting a little bit of one type of hormone, don't you want to make a lot of receptor sites so at least you know it binds? Or if you have too much hormone, don't you want to limit the amount of receptor sites so not every single time it binds? Yeah. So it gives us a chance to regulate the hormone differently. So, hormones is a protein molecule to which a particular molecule binds strongly. Responds to several different hormones. Different tissues have different combinations of receptors. Presence or absence of a specific receptor determines the hormonal sensitivity. Okay? Now, cell. has one of these and one of these, it is what it is, right? It gets it, maybe it reacts, maybe it doesn't. What if it has that many? Is that cell always going to get activated when that hormone dumps now? Yeah, what about the U-shaped one? If it comes in contact with it, it might activate, but if it doesn't come in contact with it, is it going to really do anything? No. So how many? The presence or absence of specific receptors determines hormonal sensitivity. How many does it have? Okay? And that's an important concept because if it doesn't have very many, it takes more hormones to try to find that one site to activate that one cell. If it has lots of them, well, it doesn't really matter at that point because it's going to find the cell and activate it. Hormones and plasma membrane receptors, catecholamines and peptide hormones, are not lipid soluble, unable to penetrate the plasma membrane, bind to the receptor protein at outer surface of the plasma membrane. Extracellular receptors. Extracellular receptors. Outside of the membrane. Eicosanoids are lipid soluble, diffuse across the plasma membrane to reach the receptor proteins on the inner surface of the plasma membrane. Intracellular, within the cell. Extra, outside of. Intra, within. All right? Now, why is this going to be so important? Well, first off, we have to think about a cell as this wonderful little guy, this little cell, right? But we don't want to think of it as this. And this is where we need to actually focus on, okay? Most people think, cell, nucleus. Right? What they don't think of is this. So that things can bind to the outside of it. Now, not all of them, because there are some that will actually diffuse right through. We don't need to bind to the outside. But we have to think about this wonderful little entity, a cell, that has the ability to have a lot of different things bind to it. And unfortunately, in some cases, viruses. Okay? And there are viruses specifically that like to bind to specific cells, especially the ones in your throat. Right? They love to bind to the ones in your throat. So, and it's all about receptors. Can we get into it? Can we trick that cell into thinking, hey, I need to be in here so that I can bind, so that I can take over the machinery in the cell and produce more of me? Because viruses are not living. Now, bacteria is a different story because bacteria is living. Okay? But it's all about receptor sites. And because it's all about receptor sites, we have hormones that either bind to receptor sites on the outside or bind to the receptor site on the inside of the cell. Hormones and plasma membrane receptors, well, we don't have to elaborate on this because you already know it. Rawr. Hi there. Now pick up your marker. Perfect. What is that? What is it? Did you say you're thirsty? Okay. First, yeah, direct contact. Tell her to pick up her pen. Ta-da! Okay, we already know this. There's nothing new going on. Broke it. There's nothing new going on here. You already understand what we're talking about. We're either going to bind to the outside or we're going to go through a process. Okay? bind to the receptors in the plasma membrane, cannot have direct effect on activities inside the target cell, use intracellular intermediary, to exert their effects. So we go into the cell and say, hey, do this. Process of amplification is the binding of a small number of hormone molecules to a membrane receptor. Leads to thousands of second messengers in the cell, magnifies effects of the hormone on the target cell. Okay? Amplification. Well, don't we want that cell to do something for us? Yeah, we do. Don't we want cells to grow? Don't we want cells to secrete other chemicals? Yeah, we do. Okay, this is what I was talking about receptors. Downregulation and upregulation. So now this is twice that you've heard it. Let's say it 3 more times. Down and up, down and up, down and up regulation. The presence of a hormone triggers a decrease in the number of hormone receptors. When the levels are particularly of that hormone are high, the cells become less sensitive to it. Okay? Upregulation, the absence of a hormone, triggers increased number of hormone receptors. When levels are particularly low of that hormone, the cell becomes more sensitive to it. Everybody get that? If there's too much, let's stop it. It's too much. All right? If there's too little hormones, let's make lots of receptors so at least we get a chance to have that hormone. Any questions on this concept? I love this concept. I love the idea to think that our body's smart enough to say, you know what? Too much hormone? Let's get rid of some of the receptors so we don't affect ourselves with that hormone as much. And then on the flip side of that coin, your body's saying, you know what? There's not enough hormones. Let's make lots of that type of receptor so we can actually get the effects of it. Okay? So we can actually get the effects of it. Let's make lots of those receptors. So absence of hormone triggers an increase in receptors. Lots and lots of receptors. Everybody wants that hormone. Up and down regulations. Any questions? And it's kind of boring, but it's actually kind of fun to think that our bodies are actually that smart. So you guys remember 241 when I said your bodies are smarter than you? They are. Like, as much as we want to say we're in control, we're actually not. You let your body do what it's supposed to and you take care of it, wow. It's a pretty magnificent thing. Pretty magnificent. You start thinking that way. Hormones and intracellular receptors alter the rate of DNA transcription in the nucleus, change patterns of protein synthesis, directly affect metabolic activities and structure of target cells. Includes steroids and thyroid hormones. Now, notice how they're telling you things that it does, but aren't these vague? Is it actually saying this one cell does this one thing with this one hormone? No, it's actually being vague. It's not until we actually start talking about each individual hormone that we find out what it does to a specific body part. Okay? This is vague, and this is good. This is something you need to know. What does a hormone do? You need to know that. It's vague, but it's good. We'll go into details when we get to the chapter that hormone belongs to. So here you go. They diffuse across and they cause gene activation. They diffuse across and they cause gene activation. Okay, same thing. Now, control of endocrine activities by endocrine reflexes. Endocrine reflexes, functional counterparts of neural reflexes. Wow. All the way back to the nervous system now. And I know you guys don't want to go back or backtrack, but we have to. The nervous system controls the body. It controls the body in certain ways. Do this, do that, move, awareness, function properly, make changes, and reflexes. Well, at the beginning of this chapter, I said that the two systems that control the body are nervous system and Endocrine. So here's all our similarities. Functional counterpart of the neural reflexes, in most cases controlled by negative feedback mechanism. So, Roberta, I'm not going to pick on you because you look tired. But that's okay. Mohammed, I'm going to pick on you because you don't look tired. You look bright. You're like, I got this. Big smile on his face. He's always happy to answer questions. What the heck does negative feedback mechanism mean? Roberta, if you know it, you can help him. But if you don't, it's okay. She's like, hello. One more time.
It's good for the body.
It is good for the body. It's actually fantastic for the body. Adam, why don't you help your partner in crime? You'll pass? Okay, it looks like you passed it to you. Negative feedback mechanism. Well, I'll tell you this, I'll give you a hint. Positive is amplify, 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 and then we shut it off. So negative would be the opposite of positive, so what does it do? Go for it. Regulate and maintain the body in what way? Anybody? Blood clotting is actually positive. Yeah. Anybody? Go for it. Maintaining homeostasis, you are correct, but how? Bingo, there it is. We're going the opposite direction. So when I said amplify, 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 the opposite of amplify is the other direction. So negative feedback mechanism takes the stimulus that we have and says, you know what? We're going the other way. So if you're hot, you sweat so that you cool down. If you're cold, you shiver so you heat up. It's the opposite of what's happening. Okay? It is the opposite of what's happening. So, in most cases controlled by negative feedback mechanism, stimulus triggers the production of a hormone. The direct or indirect effects of the hormone reduce the intensity of the stimulus. So now the key word for every single one of you in here, and you should highlight this key word, stimulus. Stimulus. Okay, because we're either going to be excitatory or inhibitory. We're either going to stimulate the release of a hormone or we're going to inhibit the release of a hormone. Why would we inhibit the release of a hormone? Because we got the action we wanted. Once you get the action you want, you shut that bad boy off, which is the opposite direction, which is a negative feedback mechanism. So, please do it, please do it, please do it. Oh, you did it? Shut it off. Yeah. And here they are. Endocrine reflexes, and I've already mentioned these ones before, in fact, before I even started the lecture, can be triggered by humoral stimuli, hormonal stimuli, or neural stimuli. Okay, so humoral, changes in composition of extracellular fluid, humoral. Okay, hormonal, arrival or removal of a specific hormone. So, stimulating hormone or inhibiting hormone. And then neural, the arrival of neurotransmitter at a neuroglandular junction. Where do we know of two neuroglandular junctions? Two of them. The neuroglandular junctions. So we're going from a neuron to a gland. Where do we know those? Two of them for sure. The pituitary. Nice. Yeah, the pituitary. Don't we go from the hypothalamus, which is neuro, to the pituitary, which is glandular? How about the adrenal gland? Don't we go from a neuron to the adrenal gland? Even though it's a misplaced collection of neurons, what does the adrenal medulla secrete? Yeah, catecholamines. Secretes catecholamines. Okay? So yeah, this is some pretty cool stuff, thinking how this works. It might be a little overwhelming at first, but it's actually not that bad. It's pretty fun. It's groovy. I dig it. Okay? Endocrine reflexes, simple endocrine reflexes, involves only one hormone. Controls the hormone secretion by the heart, pancreas, parathyroid gland, and digestive tracts. Complex endocrine reflexes, one or more intermediary steps, two or more hormones. The hypothalamus provides high level of endocrine control. The hypothalamus, through the infundibulum to the pituitary gland, posterior and anterior pituitary gland. A bucket load of hormones. Posterior and anterior pituitary gland. All right, let's see where we're at with time. Did you guys know it's Tuesday? Two more slides. No. Step away. There you go.